Welcome to Study Time, a televised home learning program produced by Rwanda Basic Education Board.
Hello, Senior 6 Chemistry students. Welcome back. I'm Alan, still with you in the chemistry lessons. We are concluding our topic, electrochemistry, today, and we're ending it with lesson 4, which is the action of primary and secondary voltaic cells, and unit 12, electrochemical cells and their applications. So you notice on the slide, you're having the dry cell, duracell, and the car battery. So in today's lesson, we shall be looking in details what makes up this dry cell and how does it produce its voltage, which is around 1.5 volts. Then we look at the car battery, which will be around 12 volts. So basically, today's work will be mainly on these two cells, since we already know how they come about from our previous lessons about the composition and the working of electrochemical cells. And as such, our lesson objectives are to illustrate with equations the discharge and recharging processes of the car battery. What exactly happens when the car battery gets exhausted, and how can you recharge it to gain its potential? Majority of you're having cars at home, so we're going to be looking at that. What happens if you're along the way and your battery gets exhausted? Would you crash and sleep in the car? What do you do? That is what we shall be looking at today. Then the next is to appreciate the contributions of knowledge of standard electrode potential to the social and economic development of the society. What do I mean? Almost 90% of people are having phones. Those phones have batteries. And you know their batteries can be recharged. Normally you use it the whole day, then at night you put it on charger, it charges up and the battery is full, then the next day you still use it. What principle does it use to have such a kind of property to make you use the same battery for years before you throw it away? So the whole today's lesson will be about such a kind of knowledge. Some batteries are not rechargeable, like the duracell, which you only use and throw away. So as I said, the whole chemistry of today will be about these cells. I hope you will enjoy it. I like it very, very much. But before we start on today's content, let's take a recap on the last lesson's exercise. I left you with that exercise 3. Look at it on the slide. We're going to go through number 1, then I will leave number 2 for you, but I've added the responses or the answers expected for these numbers. I've added the answers expected for these numbers. You will go through and calculate. It's a simple application of what we've been going through. So let's go through number 1 without taking much more time. We are given the half cell reactions. The dichromate is being reduced to chromium-3 in presence of hydrogen ions, and that is its potential. Then we have oxygen also gaining electrons, forming water, and that is its potential. We are to write the reaction between the dichromate ion and water using this information, applying the principle. Can we now focus on the board? I've rewritten it for easy explanation. When you look at this with our potentials, you should be in position to tell which reaction or which side will undergo oxidation and which side will undergo reduction. I pose a question. You student who is looking at me right now, which side will undergo oxidation basing on the electrode potential? Yes? Okay, now check it on your paper. So we expect this reaction to undergo oxidation because it is less positive compared to this. The principle here is the more positive becomes reduction and the less positive becomes the oxidation. So on the side of oxidation or the loss of electrons, we shall have this. So we must reverse it. In this case, we shall have water as a liquid, losing electrons. We shall have water giving us oxygen as a gas, plus 2 hydrogen ions, plus 2 electrons. If you want, you can directly change the potential here to become minus 1, 2, 3 V. Yeah, because we've reversed the reaction. And the side of reduction, we shall maintain it the way it is. We shall have the dichromate and the 14 hydrogen ions, then 6 electrons, giving us the chromate 3 ions. This is a 2 plus 7 water. This we can maintain its potential as 1.33 volts. We have these two. Remember the principle, electrons lost on the oxidation should be equal to the electrons gained. So to have 6 electrons, we must multiply by a 3 here, everything. So as 6 electrons, 6 electrons. So to get the overall, we need to look at what is the same in each case. What is the same in each case? For your case, let me first rewrite everything. Now it will require too much space. Okay, they will fit in there. So we shall have the chromate, for easy understanding for everyone to understand what is happening in here, plus 14 hydrogen plus 3 water, because this has to affect everything. The electrons will cancel. This is giving us 3.5 of oxygen plus 6 hydrogen ions. Then we add this part here, 2 of chromium ions, then plus 7 of water. If you want, you can include in the energy here, which will be the potential, which will be this one plus this together, but I will bring it later on. Let me not include it in here. Let me leave it for another step. So we have this case. You must be noticing that we are having some parts which are common to either side, this side and that side. So in the overall equation, we must eliminate this. So in this way, we shall find we are having the final, which will be chromium aqueous, this 14 and this, we can bring it in here. What does that give us? So we shall have this, then plus 8 hydrogen ions. Bringing this here, we subtract it from 14. then plus, this is 3, this is 7. So we shall take this water molecule to that side. You're not seeing that? So in here, this ends up this way. It will give us 3, 2 of oxygen gas, then plus the chromium 3 cations, then plus 4 water as a liquid. So now this is our equation. That is our equation. You see where I've brought it, or where I've calculated it from. This is for your understanding. Normally in a usual exercise or usual classwork, you may not need to show all this. You just come to here. But this is for your understanding. So, lastly, calculate the value, the E cell. E for this reaction, like as I had said, you can simply add this because we've already rotated it. It would be E theta 1, call this 1 and this 2, plus E theta 2. So minus 1.23 plus 1.33. What does this give you? And it gives us a positive 0.1 V. Or substituting the formula for reduction minus oxidation and maintain these values the way they are, you will still get that same value. So that is in terms of potential, standard electrode potential, and how to formulate equations, as we're going to see in the applications of standard electrode potential. So we've already gone through this part. So that is it. As I said, number 2 is yours on the slide. Number 2 is yours. The answers are there. Now, today's work. Other types of voltaic cells. We looked at the Daniel cell. The Daniel cell is the one which has zinc and copper electrodes. So now let's look at other cells. As I told you at the start, in objective, we have to look at the dry cells, car battery cells mainly, and even the telephone, the mobile phone cells, the computer cells, and so on. Let's start with the dry cell. It's normally called primary cell because for it, it is used once. This is a primary dry cell. Basically, it is an alkali dry cell. It is only used once. When it is exhausted, you throw it away. That's why it is called a primary cell. The alkaline dry cell, we are going to see where it comes in. So what exactly makes up this cell, this Duracell specifically? Let's take a close look at the slide. So if you cut this cell on one side, you should be able to see a zinc inner case, which is the anode. Then it has the graphite rod as electrode to allow the electrons to move, and the paste of ammonium chloride and the manganese oxide. This is the cathode. Of course, with the metal cap, which acts as the positive side. And if you look closely on it, there is a positive sign indicated. Even it is here. Look at it just on the slide. That's positive. That is the upper side. So how does it really generate the potential difference? So the zinc loses electrons. As it loses electrons, the manganese, which is oxidizing, it takes up electrons, and in the process, the ammonium ion loses a hydrogen, forming ammonia. The presence of this ammonia is the reason why they are called alkaline dry cells. So when this loss of electron and the gain of electrons happens, they complete the cell. And so they set up a potential difference. Normally, these cells have 1.5 volts as their potential difference. And as you can see, the potential difference is very, very minimal. They are only used mostly in torches and those minor activities like in cameras and so on. Their voltage is very, very low. So they are used in petty activities. And when they are done, then they are thrown away. Secondary cells. These have unique character that they are rechargeable. When the current ceases to move or it is exhausted, you can put them back and you recharge them. So they are rechargeable. Examples are the lead acid battery, which we shall stick on to match the car battery. At least almost, majority of us have seen the car battery. And if we haven't, it is just there indicated. Then we also have the nickel-cadmium cells. You see the examples are there. They come in different shapes. Do not cram that the dry cell will always, no, the cell will always be like this. No. They come in different cells and different shapes. We also have the lithium-ion battery. This is the common and the very advanced. Example is this lithium battery for the mobile phone, the smartphones, like LG, Samsung, and so on. Majority of them, they have the lithium-ion battery. Look at it. Then the laptop, like this HP, they also have the lithium, which is of this category. Now you can see the knowledge of science. If the discovery of such batteries which are rechargeable hadn't happened, what would happen with our smartphones? You use, in a day, the battery is exhausted. What happens next? You throw it away. Imagine that. What would happen to these machines where you can use for over 4 or 5 hours without being disturbed by the battery? So the development of such a scientific devices has made life much more easier. And that is the point I wanted to stress in. You can use as much as you want. You charge, take 2 hours charging, then you come back and use your gadget. So, as I said, we shall stick much onto the car battery, discharging and recharging. So what exactly happens when we say the car battery has been exhausted or it is discharged? This is what happens. Before we understand that, we need to look at what makes it up. This car battery is made up of sulfuric acid as the electrolyte. The anode is lead metal, then the cathode is lead 4 oxide. From your knowledge of chemistry, lead 4 oxide is unstable. So it easily gains electrons to form a stable lead 2. So what happens in here is when you get this battery and put it in the car, it starts discharging, losing some of its voltage. And what happens is the lead will lose electrons. Then the lead 4 oxide gains those electrons. Sulfuric is the electrolyte, as you see. So in the process, you will form lead 2 sulfate, and the electrons lost. Then the lead 2 gaining electrons, also lead 4 gaining electrons to form lead 2, which will combine to form lead sulfate. And this is the overall equation. So after using like a month or so, the battery will be discharged because you will no longer be having sulfuric acid. You will no longer be having lead producing electrons. At that moment, there will be no more current flowing. And that is the point where we say the battery is discharged. It is no longer producing enough of the voltage or enough of the current to let the car move. So it needs to be recharged. The point to note in here is the presence of the electrolyte, sulfuric acid, and the electrodes, lead and lead 4 oxide. So, normally, This car battery has the capacity of 12 volts. You see it is much more advanced compared to this simple Duracell dry cell, which has 1.5. So by that factor, it has the capacity to offer that volts for some time. And what makes it have those 12 volts is because of its structure. This pack you see is made up of 6 small cells in it. This is a cell with a lead metal and lead oxide. This is another cell, this is another cell, this is another cell, and so on. This structure fully explains it. 1, 2, 3, 4, 5, 6. This is the cell, the lead acid cell inside of this or this. So since they are 6 and each has the capacity of 2 volts, then they give a total of 12 volts. So what happens when it is discharged and we want to recharge it? Recharging is simply the reverse of discharge. You know, we still even have this work here. Take a look on chalkboard. We even have this. This way, reverse it. Reverse it. When you reverse, the potential reverses, indicating if it was gaining and you reverse it, it loses electrons. This is the principle that occurs in recharging the car battery. What happens is just, you know, some of you normally call it jumping the battery. This is the setup. Pass the electric current in your discharged battery. You will reverse the reaction and it will be new again. So the setup is get your battery, connect it to a booster battery, a battery which is still working. And this is the setup. Take note on how you do it. Step one is on the positive terminal of a discharged battery. Step 2, on the positive terminal of your new battery, or which is working, then connect it to the ground or to any other metal, which we call earthing. So when that happens is the reactions which happened during the discharge. That is lead losing electrons, forming lead sulfate, as you see here, and lead 4 oxide gaining electrons, forming lead 2 sulfate, and the sulfuric being broken down to water. So when you reverse, when you pass in the electric current, the lead sulfate breaks down at the anode, losing electrons, forming lead again. Then, at the anode, the lead sulfate gains electrons, forming the lead salt again. Then the cathode will now take up electrons, will now lose up electrons, and so forming the lead oxide, which was in the normal state. So what I'm saying in here is recharging is just opposing the discharging reactions. Just reverse them, and you'll have your battery fresh and ready to go. So that is basically the recharging. Let's conclude up with the applications of standard electrode potentials. And as we had looked at the start, they can show you which metal is a reducing agent. In other words, the metal which easily loses electrons. And so the more negative the potential, then that indicates that metal is a stronger reducing agent. Then they also show us the overall EMF for a cell. That is what we call the cell standard electrode potential in there, the E cell. You can use the standard electrode potentials to get the cell for all the cells combined. And you can predict the feasibility of a reaction. That depends on whether you need energy for reaction to occur or you don't need energy. Then finally, you can predict the outcome of a redox reaction in a solution. For instance, if you have zinc and copper, which one will displace the other? And that is what happens. So in predicting the feasibility, we look at either the reaction is spontaneous or it is non-spontaneous. Look at this example, zinc connected to copper, zinc losing electrons, copper gaining. Then another copper losing electrons, zinc gaining. Which of these two is spontaneous? From your understanding, zinc loses, copper gains, and that is evidenced by the electrode potential value, which is positive. But if you reverse, then the value becomes negative. So a reaction will occur without any external help if the E cell is a positive value. For instance, zinc and copper. This will occur without any applying any heat or any electricity. But this requires electricity to occur because you're forcing copper to lose electrons and the zinc cations to gain electrons. So that is how you can predict the spontaneity of a reaction. Finally, that is the end of that unit, and that is the unit exercise. Please, again, have some more time to look through it and understand the principles. Thank you for taking part in this lesson, and thank you for being part of this unit. I wish you all the best.